Okay, so this talk is about sketching meets differential privacy, fast algorithm for dynamic Kronecker project projection maintenance. This is joint work with Zhao from Adobe Research, Yang from University of Washington, Yuanyuan from University of Washington, and myself from MIT. So let me give you a brief preview of the problem to study here. What is the projection maintenance problem? Suppose I give you a projection matrix P, and this matrix dynamically changes for each iteration. And at each iteration, it receives think of we have received an online sequence of vectors from h1 to ht, and at each time t, we are reviewed the t's vector. And the goal is we need to maintain this projection matrix P, we need to update it, and we need to approximately output the matrix vector product of PT times HT. So for more details, let's see a version for in which this data structure is used in linear program. Suppose you're given a constraint matrix A of size m by n and a non-negative diagonal matrix W of size n by n. Think of this as a slack. The projection matrix is defined as the square root of the W times A transpose times AW, A transpose inverse times A times square root W. Essentially, the projection is onto the column span of the matrix A times square root of W. So this is one of the very canonical applications in linear programming, and you can generalize that to semi-definite programming, where your constraint matrix is a size m by n square matrix, and your W here, instead of a diagonal matrix, is positive semi-definite. And the projection is defined as projecting onto the column span of A times V, where V can be W Kronecker W. This is a primal dual central path introduced by Nesterov and Todd, or V is equal to W tensor identity matrix. This can be viewed as the affine scaling algorithm due to Kronecker. So for this talk, I will ignore the updates to W or V, and we'll be focusing on approximating the matrix vector product between a static projection matrix and a sequence of online vector. So how do we approximate this matrix vector product efficiently? Let's say, for the sake of discussion, let's suppose our projection matrix is of size n by n without any additional structure on the matrix and any additional structure on the online sequence of vectors. It takes O of n squared time to compute this matrix vector product. What's a faster algorithm to do here? The idea is to prepare T sketching matrices denoted by R1 through RT, each of size S by n. And we can batch them together into a large matrix of size ST by n. And during the initialization phase, what we do is we batch multiply this large matrix with a projection matrix. And this step takes this tmat and st time, where tmat and st denotes the time of multiplying a matrix of size n by n with another matrix of size n by st. So we will see that this leads to a very fast query in the sense that whenever we receive a vector ht, we use a corresponding sketching matrix for the t situation to sketch it down to a vector of size s, and we find the corresponding portion of the batch multiplication of the sketching matrices with a projection. And then we perform a matrix vector product of size n by s with a size s vector. So this whole procedure takes O of Sn time. And what kind of guarantee this algorithm provides us? So with high probability, we have that the approximate matrix vector product is close to the original matrix vector product in an L infinity norm sense. So we will kind of ignore the discussion on the guarantee and focusing on to get a good algorithm for this problem. The issue of the above framework is it's not a very nice algorithm when your t is very large. Think of your t as, let's say, n, or your s as square root n. So in this case, um, the number of sketches is kind of too large, and even though you batch them together, the initialization phase might be relatively slow. The reason we need to use t-sketches is to ensure that the algorithm is robust against an adaptive adversary. And the key reason why we want such a guarantee is that this data structure is usually used in an optimization process in which the input to the data structure usually depends on all the prior outputs from the same data structure. This means that any data structure that basically says that, well, we have this high probability guarantee holds for any vector or any input we haven't seen before does not work because the vector that's being fed into the data structure already depends on the internal randomness of it. So the question here is it possible to use little of t sketches while maintaining the robustness? The key tool here is to use differential privacy, surprisingly. And this has been shown in a Stock 22 paper. Basically, they say that you can only use square root t of the data structure. However, this can only handle one-dimensional outputs in the sense that you can only output a real value. The algorithm is pretty simple. So what you do is you prepare a square root t of the data structures. During the query phase, what you do is you sample polylog n of the data structures, and if you ignore this private part, you essentially run a turn-off argument and you take the median, output the median. The twist here is you use a private median instead of the median. And during the update, what you do is you simply update all the square root t data structures. So this procedure seems very simple. It's essentially a turn-off argument in conjunction with a private median. So why does it work? The short version is that it follows from a strong composition of differential privacy and amplification due to subsampling. And the longer version is as follows. So whenever you use differential privacy, you want to protect the privacy of certain database. And here, think of the privacy you want to protect is the random seeds of the data structures. Because for adaptive adversary, for the inputs that depends on all prior outputs, you should assume the adversary can learn the internal randomness of their data structures by inspecting all the prior outputs of your data structure. So it's essential for you to protect the internal randomness. And this is where the private median comes into play. The noises from private median effectively hides the randomness of the data structure. But this is not sufficient because their result can only output a single number, but we need to output a vector. How do we tweak this algorithm for high dimensional output? Um, it's not super complicated. What we do is we take the median of a bunch of vectors. There are various ways to define this median, such as geometric median or coordinate-wise median. And what we do here is just coordinate-wise private median of all the vectors. And this gives us an algorithm that outputs a k-dimensional vector with good approximation guarantee, such that it uses square root t of the data structures. And during the query phase, we sample polylog n data structures, take the private median for each coordinate of these vectors. And this incurs an extra k to the 1.5 runtime. And during the update, similar to the one-dimensional case, we update all the data structures. So when we translate back to the projection maintenance task, this means that we only need to use square root t of the sketching matrices. And we effectively reduce the initialization time to t mat n s times square root t instead of s times t. And the query time becomes Sn plus n to the 1.5 because we set k equals to n. And to give you a concrete sense of this data structure, think of the primordial linear program in which we need to choose s equals to t equals to square root n. And in this case, without using this data structure, the initialization time will take n to omega, where using this data structure, it gives us improved initialization time of n to the 2.186. And the query time is still n to 1.5 because the original s times n is n to 1.5, and the extra runtime we incur does not hurt here. So to summarize, we develop a adaptive, robust framework for data structures with high dimensional output. And this leads to fast algorithms for projection maintenance. Of course, I haven't covered the projection maintenance data structures in great details, in which you can support the update to the diagonal matrix W or to the tensor product matrix V, and how does this data structure fits into the picture of, let's say, a Nesterov-Tod semi-definite program solver. And for more details, I encourage you to check out our paper. And that's it. Thank you.